Hello, and welcome to the InfoQ podcast, a software engineering podcast brought to you by the same team behind InfoQ.com. InfoQ.com is a software engineering news site which aims to help progressive software development teams adopt new technology. We are also the people behind the International Software Conference, QCon.
All right, my name is Wes Rice. I'm the chair of QCon New York, San Francisco, and London, and we are here at QCon New York.
Hi, I'm Werner Schuster. I'm usually the brains of these conversations, but today
He is actually.
Today we have Caitie McCaffrey, and we're very happy, who is going to tell us all about what she's doing today and distributed programming and so on.
You're at a company called Twitter, right?
Yeah, a little company called Twitter. You may have heard of it.
Yeah, once or twice.
So I've been at Twitter for a year and a half now, and based in San Francisco. I was, for the last year and a half, the tech lead of the observability team, so all the fun monitoring, alerting, distributed log aggregation, and tracing to help all the Twitter developers keep Twitter up and running. But I recently just changed positions.
So what's your new position?
So I just joined our engineering effectiveness team to do distributed build systems. So the whole the purpose of my group at Twitter is to help make dev tools better and help make our developers at Twitter more efficient and happier. And so we're taking build tools, if you're not used to them or haven't thought about them deeply, which I honestly hadn't until I joined this team, is when you use your build tool and tell it to compile your code or run some CI and check in your code to whatever repo you happen to be using, or run some test cases, all of those kinds of things. We do all of that great stuff at Twitter, and we have teams that support it. And so what we're trying to do is, instead of having these different silos, which is build, which is our Pants team, and Pants is open source, so a lot of people may know of it, and you can go look at it and play with it, or our CI pipeline, continuous integration, where you write some code, and then you want to check it into the mono repo, and so you submit a patch, a build to Git, and then we use Jenkins, and that will run your job, but then we'll also farm out the tests to be, all the tests in the mono repo need to get ran. And so since we have one repo for all of the Twitter code, there's a lot of tests that need to be ran. And there's a homegrown tool called Iron that can distribute all of that code, or distribute all those tests to be ran. And so it does run in a distributed fashion today, but it's very specific to that instance. And so what we're trying to do is, my team is trying to make infrastructure so that not every team has to solve the distributed problem on their own, and also give developers some APIs and tools that they can build systems very easily. You don't have to get into the muck of all of the Linux file systems and be a Linux expert to write a developer tool. And so that's a really exciting project. It's very new, and there's a couple of us working on it, and we're hiring. So if you want to join me and my team, you can come do that. But it's really exciting for me personally, because it's an area that I am less familiar with. I've always been, large scale data ingestion and millions of requests per second and things like that. And this is, much lower scale, because it's, build jobs or running tests, but they take a long time. And so it's sort of this flip inverse problem where you have less requests but longer running jobs. And so that comes with a whole new set of challenges that are really, really interesting.
So tell us about some. What are some of the challenges?
So one of the challenges that's super basic is, typically we use timeouts to detect failures in distributed systems, right? You might say, if I don't hear from you in 100 milliseconds, I'm going to assume the request failed and you died and whatever. When a job maybe could take an hour, you can't have a timeout, right? And so there's different types of things you have to do. We're going to use a lease protocol and implement that to say, not only is the person who's running the job still around and waiting for the request, but is the runner around and still working on my request, right? So that we can have this periodic check-in. We're also using the Saga pattern to sort of, jobs generally have multiple tasks that you want to execute in them, and Sagas is a way to do distributed long-lived transactions. And then I've talked in the past about how you can use them to do distributed transactions without atomicity. And so we're going to use Saga pattern to ensure that all of the pieces of the job run correctly, even in spite of failure, right? So that's really interesting when you start thinking about this long-lived workload in a distributed system.
So what are the APIs that you're building? What other things can your developers look forward to? Spoiler alert.
Spoiler alert. So some of the stuff I'm personally just working on right now is a scheduler The Saga stuff will happen. Also, all of this is being built to be open source specifically. Okay. So I'm going to be really excited when we can like officially put it out there. So that'll be great. And then, you know, I think the other core component, which other members of my team are working more heavily on, is this idea of a snapshot. And so a snapshot is a core input into the system. So instead of just operating on files and having to deal with all the muck of messing with the Linux file system and copying things around, and like that assumes that the file is on the box, right, which could be problematic in a distributed case. It makes it difficult to distribute the load. We just give you this concept of a snapshot, and you say like create a snapshot from these files, and then we magically take care of storing that wherever it needs to be, and then another box somewhere can reference that snapshot. Another core concept is snapshots are immutable, so that you can start building tools that like functionally compose together instead of just mutating files on a single box, which is how a lot of built tools work. So we're sort of approaching this almost from a very like programming language functional concept with some distributed systems built in, so that the end game is, you know, like if you're at Twitter and you're working and you are offline, everything will run, you know, while you're disconnected, because we want you to be able to like, you know, work on an airplane or something, which is, I do that a lot. But we also want you to be able to, as soon as you know, hook into the VPN and onto the network or whatever, and have your credentials authenticated, that then we can make your build go much faster. And maybe like the goal is like run linters in the background, or run, you know, I mean, this gets a little into verification and like researchy stuff, but like what if we could run verification of your system for you in the background and tell you like as you're typing that, you know, you kind of like this is going to cause a problem. That's sort of the end game. So we want to be able to enable developers to make all of these great tools that help you write better code and like do all this like, you know, stuff that you don't want to have to spend time thinking about. You just want to think about solving the problem that you're solving. Really fast and really easy to maintain, and not take, you know, like a whole like team, a pizza-sized team to support and do the operational cost of. It should just be, you know, we provide this infrastructure and then everyone can just plug into it.
Very cool. So you had a tweet, I guess it was probably, I don't know, 4 or 5, maybe 6 weeks ago, something like that. And it basically was, I'm paraphrasing, so you'll have to forgive me, but it's something like, don't ask me to speak at your conference because I'm a woman. I have much more interesting credentials than that.
Yeah.
What any comments or what? There was, I think there were like hundreds of retweets off that. It obviously struck a nerve somewhere.
Yeah. So this is one of the things, and I get asked. I speak a lot. I get asked for jobs a lot. I'm sure like a lot of developers can sympathize with the inbox of just like random job requests. And a lot of times, you know, and I think they're very well meaning when they're sent, but they say, you know, like, oh, like you're a fantastic like female engineer, or like we really want to have more women at our conference. And it's sort of like, okay, like I applaud you for like trying to get to taking diversity seriously and reaching out and trying to get more diversity, which is not just, you know, white women like me, but also people of color and women of color into the field. But it's also like, if you take a step back and think of it, and this is a little bit of empathy coming in from like my point of view, if you're asking me to speak because I'm a woman, that's saying like, hey, you do all these things, but like really we just want you because of your gender, which is kind of weird, right? Because like I am in this field not because of my gender, but because I like doing things in technology.
Yeah, super disingenuous, yeah.
And I think a lot of you know, I mean, and so it just sort of strikes this weird nerve where it's just saying, you know, it has a lot of weird implications, which I don't think is meant by any of the authors who send these, which is like, hey, we're just like, it's like affirmative action where we're just recruiting you because like, and we're lowering the bar to get you in. But these are all like conversations that are happening. And so I had gotten a couple, I don't know, something struck a nerve that day where I'd gotten something recently where they're like, oh, we want you to come speak because you're like an excellent female speaker. And I'm just like, oh gosh, okay. So I like fired off a tweet, and then I like actually went offline, and I came back and I was like, oh, whoops. Okay. I guess I struck a nerve. But I think the reason it got so retweeted and there were so many like women responding and being like, yes, was because it happens a lot. And I think it doesn't like feel great when people are asking you to do something that should feel great. Like, hey, we really value your opinion and want you to come talk and educate people at a conference, or like we think you have great skills and would like you to be a part of our team. And so I think it's just one of those like well-meaning things that does more harm than people think it does. And so I just meant to say that to sort of say, you know, like think about it from our perspective, and like we can do better, right? Moving forward.
Yeah, I think the empathy is a good way of thinking about it. Put it from your viewpoints. That way you can really understand the way it's being phrased.
Totally.
It's a tough problem, right? Because there's underrepresented groups. It's not just women. There's all kinds of underrepresented groups, and they definitely need to we definitely need to make sure we're all being very inclusive in the way we're thinking. So I think empathy is a great way of phrasing it.
Yeah, and I think the real test, and I've sort of told people, is this the one test. If you're going to say it, like, hey, like, we want you to do, like, some women's thing, whatever, wherever you're putting woman or female gender, just replace it with, like, male or, like,
and does it still
dude,
sound like
and does it sound weird, right? Because then it's probably like, hey, maybe, like, let's step back and think, like, oh, maybe it sounds weird to, like, the person who's receiving it,
There's
right?
a smell there, yeah, absolutely.
Are there any, maybe I'm doing the same thing now, are there any resources where people can go to find people of different women or underrepresented groups? I'm asking you, obviously.
Yeah.
Am I making the same mistake now, or?
No, I mean, I think it's really fine to ask. I think a lot of people are going to say, they may not be able to help you. I mean, I can help you with my network, which is, like, that's, like, what I know. I know my network has deficiencies, so I do try and reach out to, like, fill it in with, like, the underrepresented groups in my network. I really actually just think a lot of this comes down to a networking problem, because people are like, oh, there aren't, like, XYZ group in tech. And I'm like, well, like, look at the Techies project that, like, Helena Price just did. Like, there are people, like, of all different backgrounds in tech, right? She found a lot of them, like 100 of them, with very little, like, searching. And just in San Francisco. Like, she didn't even go outside of San Francisco, really.
And we should mention you were one of the featured.
Yes, I was in Techies, which was very good. It's a really amazing project. It's super awesome project. If you don't know about this, just, like, Google Techies project, and it'll come
We'll
up.
have show notes at the end, so we'll go through and put show notes. That
I think I shared on my Twitter, and I don't know the link offhand, but there's a Google Drive that is open and free to the public of, like,
great references.
Hundreds of papers on diversity in tech and the workplace and reasons why you should care and, like, how do you get more people. And these are people who actually, like, study this and, like, it's their job to do this, whereas, like, I just happen to be one of those people. So, like, I don't actually know anything other than my anecdotal experience. And then there's also, like, a ton of, like, people that you can actually hire to do this and be diversity consultants and are actually really great at this. So, like, I totally encourage people to go do that as well.
Sure. So tomorrow you are going to do a talk on verification of distributed systems. That's kind of tied to your ACM paper that you did, or article that you wrote about a month or two ago. No.
Well, I mean, I wrote it in September.
You wrote it like last year, but yeah.
I got published in ACMQ in November, and then in the Communications of the ACM in February.
Okay, so I read the one in February.
Yeah.
So can you tell us a bit about, I guess, what you're going to go into in the talk?
Sure. So the motivation for this article, which you can actually is available free online if you want to read it, or watch my talk here at QCon, is I just think testing in industry is, like, not a skill we're great at across the board. For a variety of reasons. And then, like, I think a lot of people sort of hear that academia is this, formal verifications is how you test things and verify things. And I think a lot of people are just like, well, I'm not going to do that, which is fine, because, like, I don't write formal verifications for, like, anything I do. I think they're interesting, and, like, there's a lot of interesting research and work being done there to make them more mainstream. But, like, I don't do that because it takes a lot of time. And so the goal of this talk was sort of, touch on that in case people actually don't know what these are. Or haven't seen them, but then also to go into like here's what we can do. It's not like a provably correct system, but here's methods where you can increase your confidence in your code, and here's some research that maybe supports that doing these things actually yields larger returns than you might intuitively think. And introducing some new stuff that's actually fairly low investment, I think, or it's not new, right? But I think it was, like, new to me a couple of years ago and new to a lot of people I've talked to it about. And a lot of strategies on, like, here's, obviously we have budgets and we have project deadlines. And so, what time do you have for testing? Like, here are some options to increase your confidence that your system's going to do the right thing.
So the phrase formal verification can be unapproachable at times, particularly for someone who's not involved with distributed systems, right?
Totally.
So you start talking about verification of distributed systems, and certain people may start tuning out. So what do you really mean? When you're talking about verifying systems, I mean, you're talking about unit tests, integration tests, you're talking about things that people are very familiar with, right?
Yeah. I mean, and so this is sort of my, like, side note, and I start a lot of my talks these days with it. We're all building distributed systems, so, like, distributed systems really aren't that scary. People have been doing it for years.
Just the phrase,
It's just like, you have multiple computers that talk to each other, distributed system. All your clients, distributed system, right, or part of the system. And so, the things I talk about, I'm going to talk about my talk, are unit integration tests and some actually really interesting research that came out recently about, like, these are super valuable, actually, and areas to focus on when you're doing this, that you can get the most value back. where they found bugs in real world systems. Property-based testing, which I think is super cool and, and is kind of like the industry, or I don't know if it's like the industry version of like a model checker, which is like a formal verification method. So it doesn't give you provably correct, but it does exercise more of the state space of inputs. And then, fault injection testing, which is really great. That's just the simple concept of introducing failures. And each of these, there's a wide range of investment you can make in them. And so the goal is sort of to say, like, if you have a super core piece of infrastructure, maybe like a self-driving car, and it totally can't fail. Maybe we should be doing formal verifications of self-driving cars, but like whatever, right? Like, I don't know, like you should probably like test that a lot. And then, if it's just something that it's like a button on a page and if it doesn't work, like you don't care and there's no revenue tied to it. And it's like sad if it doesn't work. We don't want it to fail, right? But like if it doesn't work or it gets kind of broken, like not that big of a deal, then like maybe you don't spend as much time. Maybe you just throw a unit test on it. Like, I mean, there's like a whole range. Like there's no one right answer. I'm definitely not like one of those people who, is like test-driven design and we're going to write 100% test case coverage because like maybe it's realistic for your project, but it's not realistic for every project, right? I don't think there's one prescriptive way to make code or make good, successful technology.
So the academics who are listening to this out there, obviously on the way to work.
This is where the smart guy in the group comes in.
Sure. Let's say I put on my academic hat. So, but I spent, we academics spent our lives building all these formal verification tools. Are these for naught? Are they never going to be used by the industry?
So I think formal verification is actually really interesting, and like Amazon actually used like TLA Plus to verify a bunch of their core infrastructure pieces like S3. So when you're building something that like a lot of people are relying on, and maybe you're charging money for people to like rely on them in a very like data intensive way, they did that. There's actually, and I think like Coq, which is maybe less known to people, is another one that actually you can write your specification and it can generate code in Haskell or OCaml. Maybe not Haskell, I might have said that wrong. I know it definitely can generate the code in OCaml because that's been done, and there was a couple Popple papers this year about this. It is a limited subset of what you can actually do in that language, but than like what we're used to with a lot of our languages, but there's advancements being made to like make it more expressive. And honestly, like long term, and then like another really interesting project is like Diego, who wrote the Raft paper, is now at Salesforce, and he just released this thing called Runway, which is a formal specification tool that in like I believe it's written in JavaScript or for JavaScript. I haven't had time to play with this. This like literally just came out in the last week, but it's cool because it's formal verification being developed by an industry team, right, and released in open source so that we agree that like being able to write something that's provably correct is very, very powerful. And if you think like 20 years down the pipe, maybe 10 if we get there really fast, wouldn't it be cool if you were literally just writing formal specifications and it generated the code for you and that code ran and it was provably correct? Like pipe dream, right? I mean, like that's the end game, right, of a lot of this research. And when you look at a lot of that, like that community that's actually going on right now, and we're actually not that far away from it because there's like a paper at Popple that was I think it was a 2016 paper or 2015, I can't remember, may have been this year, where they like literally wrote a database and then generated the OCaml and it like works. And so it's like limited, it's not doing everything that we're used to doing, but like we are getting there. And so I think this area of research is really powerful because it starts allowing us to do things better. You don't have to invest all this time in, testing and verification and bugs if you're just writing. The computers are generating code and they're probably like better at it than we are at writing it once we build the tools that are smart enough to do that. Because they're using like math and type theory and stuff to prove that things are correct. So I think there's a lot of really interesting research happening there that gets me super excited. But yeah, it's like definitely down the road. So I hope the academics keep doing that so that I don't have to, spend all of my time. Also, like for the people who are industry who are just like, that sounds terrible and I really like writing code and I never want to live in this world, you don't have to be on call in a system that's provably correct because it's going to have way less bugs and outages. So that's really cool too.
Yeah, forcing people to be on call and have a pager. Do kids still have pagers today?
I mean, I have pager duty on my phone.
Oh, okay.
So it's kind of like a pager.
I get Snapchat at 3 a.m.
Snapchat?
You can Snapchat it when your system goes down.
Forcing people to do that.
I didn't know they branched out into the alerting field.
So we talked about academia, but there's a whole community of model-driven development people. do you have an opinion about what they're doing? Because they're basically saying the same thing. Build your model, then it says there's a green checkbox. This is okay, and then it says gives you code.
Yeah. I mean, I think people should use. Once again, I don't believe that there's any one prescriptive way to like build code. You have to work with what works for you and your team and your business. I think if you can generate code, like we already use code gen pretty effectively today, and that's not that old of a tool, right? When you think about it, I think it's like 4 or 5 years since code gen has become very like effective and useful and more broad. This is just another form of code gen. It's just more like widely distributed. So I think, and I definitely think for things that are very, mission critical, like doing formal specifications is interesting. I mean, actually, in this book that Leslie Lamport wrote about TLA Plus, he actually says you should, it's a good idea to design a system, I'm paraphrasing, design a system before you implement it. You should write a specification before you implement it because it actually forces you to think through all the things. Even if you're not going to run it through, writing the specification is step 1 of formal verifications for people who haven't done it, and then you have to run it through a model checker or a proof assistant to help you actually prove that it's right. And so doing that even without even just actually going through the second step of proving that it's correct is actually useful. And they call this out in this paper that a technical report that Amazon wrote about using it, where a lot of the bugs were actually just found while writing the specification because they just realized they had missed something. Yeah. I think so. There's a lot of value, especially when you're doing very complex distributed systems where you have a bunch of asynchronous messages, and we're talking about different levels of consistency, which gets way harder. When the world is not just linearizable, a lot of things are happening. You have to hold a lot of stuff in your brain. So formally writing things down in logic and proofs, which is maybe a little different than what we're used to, can be very, very helpful, I think.
But so the problem is, of course, with what you just said, is that you have to, and I think Leslie Lamport gave a talk at QNSF a while ago. His basic message that I got was that you have to think and understand your problem before you code it.
Yeah.
Which is not very popular because I just want to bash away at my keyboard.
Yeah.
So, I mean, I looked at stuff from, NASA and people like that who write, as we said before, code that has to work, otherwise things go boom. And if you look at what they do, is they basically they spend 3 years on it and go over every line of code with a fine-tooth comb, and that's not very popular. So we want a tool that I push a button and it tells me I'm okay.
Right.
And that's not going to come, I suppose.
I mean, actually, I don't think we're super far away. I think you may not be able to write so a lot of this is predicated on if you want to write code like you're used to writing code and then do a specification on top of them, run this code through a thing that tells you it's correct. This requires a stronger type theory or a type system in a language. So something like Go or JavaScript or Python, these things that do not have types, they do not live in this new world of run my code through a formal method to detector unless someone's actually doing the work to build a type system. Or infer the type system on top of it first, which there actually is work on some of these dynamically typed languages to do that. So you may be able to write in that language, but it's more work, right? So you have to have the type theory first, and there's a lot of advancements being made there. And then you have to go and then have the formal verification on top of that. So there's actually this interesting system, which Inez Sombra is going to be talking about at the Papers We Love /QCon event tomorrow night, called Iron Fleet that came out of Microsoft. And I'm not, so I believe the crux there is they have this language Daphne that they can build on top of, and then when you're typing in your IDE, Visual Studio, then it'll go and send updates to the cloud, and in the cloud it's running these this type theory, it's running it through specification, and it'll actually tell you and do the red squiggle to say, hey, your thing is no longer safe, right? You just wrote some code that's gonna break. And that's the dream, right? Obviously it's not fully there, but it's really interesting research to start thinking about hey, maybe we can build tools around languages that people already know or just slightly modify them. The biggest barrier in this space is basically the constraints on what this actually works on top of. How expressive can the programs we write be? Because we can already do some of this, it's just that you have to very much limit the expressivity of the language that you're using to do it. So it's can we open up, the full repertoire of code? How wide open can we blow the doors on the repertoire of code that we can use that we're used to programming in?
What's interesting also to see the rise of something you mentioned before, property-based testing, which is kind of a halfway solution, kind of I'm going to use the word stochastic because I think it sounds smart. I'm not sure what it means, but it's sort of like halfway between formal verification and hacking it.
Yeah, so I think property testing is super useful. Quick check, and then like Scala check is one that runs on the JVM. Quick check was the original one, and John Hughes wrote that, and the idea, and that works for Haskell and Erlang. The idea there is that you define properties about your system, so you're once again writing logic, and then it'll generate, and then you can combine properties to build actually like really complex test cases, basically. And it'll go and generate a bunch of random input into your system when you run these tests. And then if it finds a counterexample to your test, it'll actually report it to you. And so that's super valuable because you're exercising. The biggest problem with testing is that like when you write a unit test, it's only exercising like the state space of the input that you like hard code into the unit test. So if I'm like doing a test for add and I only test at like 1 + 3 = 4, then like I only actually have proved that those inputs produce that one output, as opposed to saying like all of the inputs in the natural number space produce correct outputs in the natural number space, or like what if we wanted to go with irrational numbers, right? Like, I mean, so it's all defining, that level of specification. And so you go and define these things in a property-based testing tool, and it's sort of like a model checker, but it's not going to explore the entire state space. So you can't say it's provably correct, but it will explore more of the state space in a unit test. And I actually think once you get used to sort of defining this kind of logic, it's actually just it's pretty low investment. It's about the same cost, I think, as writing unit tests. And like this has worked and found very large bugs in systems like React used it. Their distributed database used it to find bugs. And they have a couple really great talks about how you model property-based eventual consistency. I believe they just found, John Hughes just gave a talk, and I'm forgetting what car company it was, but they found a bug in the car software doing that. And I don't think it was like a catastrophic bug, like the car was going to like blow up or anything, but they found a bug, right? And so that was like they were able to then fix this bug in the software. And then I believe he just also gave a talk about how they found a bug in like Dropbox as well using property-based testing. And so you can find some of these really gnarly bugs because you're combining you're doing a lot of the different, it'll generate a bunch of input, right? And also like combinations of input instead of just doing, if you could define a large set of properties for the whole system, then it'll like do multiple, like all the different variations of input and give you the counter example so that you can then go fix it.
So it's basically a realistic check. You don't go through all the states, but you hope that you can customize property-based testing generators to look for interesting areas, basically.
Yeah, I mean, the goal here is you're just exercising more of the state space and hopefully like more combinations of the state space than you would otherwise. And so while you're not going to get, like, if you think of it like a circle of like all the state that we could possibly ever hit, like maybe you'll hit that sooner instead of like that one weird off case in production, right? Like when like the stars align and these 3 weird things that are never supposed to happen, and then like your code blows up, right? And causes like, and that's like the stuff that kind of is causing like major outages these days, because we're having multiple inputs, like 3 or 4 inputs in weird situations across a system that are causing like these complex failures that were like never thought of, right? I mean, this kind of goes back to, and I think John Alsbaugh talked about it this morning a little bit, we're building really complex systems, and it goes back to how it generally takes multiple failures. We're pretty good at catching the one thing failed and it doesn't cause the system to break anymore. So we've like done that, and that's really good, because we used to like, Leslie Lambert said back in the day, like a distributed system is one where a single computer can fail and that you didn't know about and like break your computer basically. And like, we're not there anymore, right? Like that's not acceptable, and that's fine. But where we're starting to have problems is just like, and this is just because of how much information you can hold in your head at any given point in time. Sure. It's no like failing of a single human being. Is, these multiple systems are failing in ways that like we didn't think of this one combination, because you have factorial explosion, and so you can't think of all of them. And so property-based testing and things like that and help you exercise more of that state space.
And this is the kind of thing you're going to go to tomorrow, right? We're going to talk about property-based testing, canary builds, integration tests, things like that, right?
Unit tests and fault injection, which is basically like proving your system to fail. And then I'll also talk about some interesting research that I think is like future thinking. I think it gives me hope. I hope other people like think that. I think some people were like, oh, I walk away and it makes me sad that it's not available today. And I'm like, yeah, but like maybe in a couple of years it will be. Like that's exciting, right?
So you mentioned that every system nowadays is a distributed system.
Yeah.
Even a web browser, obviously it's a distributed system.
It's talking to something, right?
Yeah, there's always something that can fail. It's out of my control. Do you have an idea of how we could get into a mindset of manually figuring out whether our distributed systems are incorrect. So I'm basically trying to ask, how can I basically become like Kyle Kingsbury and torture distributed systems on my own?
Yeah, I mean, and so I'll go into this a bit in my talk tomorrow, but I think a lot of it is like, designing it, understanding where your dependencies are, and then like actually fault injection. So Kyle Kingsbury's tool, Jepsen, that you alluded to, is a class of fault injection tools. It interjects faults into a system under test, and then he he's basically just stressing and interjecting a lot of faults and then watching the results of a system under test. And so obviously it's a very sophisticated fault injection system and analysis tool to prove that all of the consistency gains are held. But like, we don't have to build something like Jepsen, or you don't have to run Jepsen to do that. You can literally say like, hey, like I know this web service talks to this database, and like what happens when I kill like a node, the connection to that, like maybe it's a distributed key value store, so there's like 3 replicas in the database. So, like what happens when I take down one of them, or like does it fail over to the other DC? And so there are low investment ways that like literally if you can design your system, or like I take inspiration from Peter Alvaro's paper on lineage-driven fault injection, or his tool called Molly that he talked about at QCon London actually, which is a really great talk about how they implemented this at Netflix. But the idea here is, instead of like exploring the entire state space of all things that could go wrong, because it may not actually affect execution, is reason backwards and say like, okay, here's a good execution, like I was able to durably store some data, and then read it back correctly. What path did that data follow to ensure correctness happened? And then you just start attacking like routes along that path. And you can draw these diagrams, like he has really great diagrams in the paper. And so if you, in your own system, if something's really critical, you must sit down and draw these diagrams that's like of my protocol, or of like where machines are talking to each other. And then like literally just go inject some faults into your system by like kill 9ing a node or whatever and seeing what happens. Like that's a really simple way to prove it. I think a lot of failures happen because we didn't think the failure was going to happen. Like we didn't think about it a priori, and so we didn't plan for it, and therefore like our code doesn't handle it correctly. Yeah. So just sort of doing that extra due diligence at design time, I think, is actually really, really useful. I always joke and say like I don't write any code that's actually really hard. I just like think a lot about things and then design systems that are hard, and then the code I write is generally pretty easy because the algorithm is mostly in how the systems are communicating, which is just send a message over TCP. That's like not hard code to write, but it is hard to design systems that are correct when we have all this asynchronous messaging and partial failure happening.
If you like what you heard, you can read Caitie's paper on ACMQ, ACM communication, either one of them. And you can also catch her talk that will be on InfoQ in the next couple of weeks following QCon New York. So thank you for your time, Katie.
Yeah, thanks for having me.